Hello all of you. Welcome to the 10th lecture in the course on analysis and modeling in chemical engineering. In this lecture, I will continue the discussion on fundamental laws and concepts in chemical engineering, and I will discuss the laws of chemical kinetics and chemical equilibrium. What I will like to emphasize again when we discuss chemical equilibrium in particular is its relation to thermodynamics that we have just discussed in the previous lecture, right? So, this is where we are. We have already covered the equations of motion, transport equation, material balance, energy balance, and last lecture we were discussing about thermodynamics. In particular, we discussed about energy functions E, H, F, G, and then different differential relations for dE, dH, dF, dG, and so on. We discussed when to use which energy function and things of that sort. Right? So, today I will switch gears and talk about systems where we have a chemical reaction. Keep in mind, in the discussion on thermodynamics, we are not specifically looking at systems where a chemical reaction is taking place. Right? So, now we focus on systems where a chemical reaction is taking place and where the chemical kinetics laws do apply. So, what exactly is a chemical reaction? Right? So, we will formally define the chemical reaction as something that takes place when a detectable, that word is very important, detectable number of molecules of one or more species lose their identity, and I mean a chemical identity, and assume a new form by change in the kind and number of atoms in the compound, and or by a change in their structure or configuration of these atoms. Right? Before I talk about what exactly is a chemical reaction, let us take some examples of what is not a chemical reaction, although typically written sometimes as a chemical reaction. For example, if H2O gas is going to H2O liquid, there is no change in the chemical identity of the molecule. Both are OHH. In fact, the bond length and the bond angle also do not change significantly between the gas state and the liquid state. It is definitely a physical change. In fact, it is a change in the entropy of it. Gas state is a higher entropy, liquid state is a lower entropy. It is a change in the physical state, but it is not a chemical reaction because they do not lose their identity. Overall, you see a change in liquid to a gaseous state, but at the molecular level, there is no change in the chemical structure or the chemical entity of OHH, that is water. Second point, it has to be detectable. If, for example, I do something like this, so I can write the benzene ring in various ways because the double bond is kind of delocalized within the ring. So, I can write this structure or this structure, and I can in principle define a transition between these two states, but that does not make it a chemical reaction because this kind of a change is not detectable. In fact, these two forms, whatever I have drawn here, are purely hypothetical in nature because in reality what you will see is a delocalized cloud of electrons, and that is typically represented by something like this, right. So, although in writing it may look like a chemical reaction, but it is not, because there is no way to isolate, for example, something like this versus something like this, or even to detect something like either of these, right. It has to be something where you see the electrons are delocalized, neither in this state nor in that state. Right? So, these are some types of the chemical reaction. We can have a decomposition reaction where a larger thing decomposes into smaller things. We can have a combination reaction where smaller things combine together form a bigger thing. Let us say if you burn polyethylene and you get back the smaller monomers that is used to create it or different gases, that is a decomposition reaction. Or if you combine polyethylene and they add together to form combined ethylene, they combine together to form polyethylene, that is the combination reaction, right. Isomerization is something where you, let us say, go from a cis state to a trans state. That change is detectable because you can identify what is cis, what is trans. They have different properties, let us say dipole moment, right. So, a cis to trans isomerization can be considered a chemical reaction, but something like the examples I showed earlier, they do not classify under chemical reaction. So, now whenever we have a chemical reaction, we have the idea of this activation energy and some energy change in this particular reaction. In fact, one of the earliest theories of chemical reactions, in fact, it is still in use today. It is called the collision theory, right? And it has its limitation. I will come to that. But what it states essentially is two molecules, they are going to collide. I give an example of carom board and pieces where it hitting each other, something very similar to that, but now the additional thing is that a chemical reaction is taking place, right? So let's say two molecules come and collide. You can imagine them as balls, as I was telling earlier, and after collision, of course, they exchange momenta, but this collision process may result in high energy because of the kinetic energy of the collisions, right? And this energy can basically transform these molecules, which is now what I call as reactants, into some products, right? So let us say here A plus B can go to C plus D. But for this to happen, the collisions must have sufficiently high energy. And the threshold where this happened is called the activation energy of the reaction. So, if the energy happens to be higher than the activation energy, then this reaction will take place, right. So, reactants A and B otherwise are in some kind of a state where energy is small, right, and they prefer to remain in that state until they get a very high energetic push. They will remain in the state of A plus B, let us say, and once the collisions give rise to large energy more than this activation energy barrier, then in that case they can go from here and become products. And in fact, the reverse is also possible. The products also can get activation energy now equal to this plus this, and that can again go back to the reactant, right. Gibbs free energy change, on the other hand, is the difference between the energy of the products minus the energy of the reactants, right. So, we can of course define all kinds of energy changes, enthalpic changes, Gibbs free energy change and all those things. But if I talk about Gibbs free energy change, that is the Gibbs free energy of the products minus Gibbs free energy of the reactant. All right. So, now we can define something called a rate of a chemical reaction. And a typical language, at least for chemical engineers, it is not new. Whenever we have a reactant, we call the rate as the rate of disappearance, right. But the rate typically is defined as the rate of formation, right. So, in order to basically keep our definition neat, what we do typically is put a minus sign over R A. So, R A in fact is negative, that is the rate of formation is R A. So, it is negative because A is getting consumed, but minus R A becomes positive. So, minus R A is positive for the reactant, and now it is not the rate of formation, it is the rate of disappearance, right. So, whenever I refer to R A without a sign, I am referring to the rate of formation, that is negative of course for the reactant. So, when I say minus R A, it is referring to rate of disappearance of a particular species, right. It is defined as the number of moles of A that lose their identity per unit time per unit volume in moles per liter second or whatever units, moles per liter hour and so on, right. Of course, if you have catalytic reaction, in that case you may choose to define it rather than volume, maybe per unit weight of catalyst, and the units will be moles per unit kg of catalyst second and things like that. But in general, if the reaction is homogeneous, uncatalyzed, then in that case we use moles per liter second. Now, for a general reaction, apart from the species participating in there, what appears also in the equation are these stoichiometric coefficients for the reactants and the products. Let us say, for example, you have the reaction N2 plus 3H2 giving rise to ammonia 2NH3. We have done that example in the first week. So, here stoichiometric coefficient of nu of N2 is equal to 1, actually with a, and nu H2 is equal to 3 and nu NH3 is equal to 2. This is like the number of molecules or moles participating in a reaction. And by simple stoichiometry, we can relate the rate of disappearance of the reactants and the rate of formation of the products. They are equal if we divide them or normalize them with the corresponding stoichiometric coefficient, right? So, in this case, for example, minus R N2 by 1 is equal to minus R H2 by 3 is equal to R NH3 by 2. Now, typically in a chemical reaction, there is going to be one limiting reactant that will get exhausted sooner. Let us say, for example, you have a reaction A plus B to C. So, 1 mole of A is supposed to react with 1 mole of B. But let us say you have 1 mole of A and 2 moles of B available to begin with. What is going to happen is 1 mole of A will be exhausted, but still you will have 1 mole of B left in the reaction, but it cannot react because there is no A available. So, in that case, A becomes the limiting reactant. So, typically the limiting reactant is chosen as the basis, and many a times it is preferable to then divide whatever equation we have with the stoichiometric coefficient of the limiting reactant, right. In the example I have shown, the A is the limiting reactant, but the opposite may also be true if B is present in a smaller amount, right. So, whatever limiting reactant is typically chosen as a basis, and typically it is a practice to divide by the stoichiometric coefficient of this entire reaction, and we represent the reaction something like this. So, let us say, going back to this reaction, if for example hydrogen was the limiting reactant, then what we could have done is divide this by 3, and we would have 1/3 of N2 plus H2 giving rise to NH3 with 2 by 3, right. On the other hand, if nitrogen is limiting reactant, then in that case we will keep the same reaction as it is, right. And of course, it is a reversible reaction. So, if reverse reaction is more favored, then we write it differently, right. So, all these things are possible, and this is how we typically represent the chemical reactions. Now, there is a notion of rate laws that is typically found from experiments, right. Rate law basically tells you how the rate of disappearance of the reactants or the rate of formation of products, how they depend on the concentration of reactants and products maybe, right. And in most cases, these rate laws are empirical. They have to come from experimental data, but nowadays people are also getting them from quantum chemistry kind of calculations, right. But mostly all the rate laws that you see in literature are probably coming from like the experimental studies. So, reaction rate is a function of the properties of the reactant and the conditions such as temperature, pressure, catalyst and so on, and that is what is called the rate law. And in the right, I am giving you some examples. These are typical rate laws. This is somewhat atypical rate law. The first one is an example of what we know is a first order reaction, because concentration is raised to the power 1. Second one is an example of a second order reaction, because concentration is raised to the power 2. Third one is an example of a zero order reaction, because there is no concentration appearing there. The last one, we cannot write it in terms of the order definition I have given. In this case, concentration appears both in numerator and denominator. Maybe some reversible reaction is happening or what not, but it cannot be expressed as a simple power law, right. But what is always true is rate law is actually some kind of an algebraic equation. One should not think of it as a differential equation, although we have defined it as something like number of moles of A that lose the entity per unit time per unit volume. It may give you an impression that I will divide the number of moles of A by volume, and that will give me concentration, and I will express the rate as the change in concentration dCA by dt, but this is not the definition of rate. dCA by dt is not the definition of rate. In fact, we can think about examples where concentration is not changing, but reaction is still happening. For example, we have a CSTR and we have steady state. So, in the case of a CSTR, you must recall that the concentration of the reactant is equal to whatever is the exit concentration. So, concentration inside the reactor is all across uniform, and this concentration is equal to the exit concentration. So, at a steady state, effectively concentration of A is not changing inside a CSTR. So, if I use this expression, it will wrongly suggest that Ra is equal to 0, that means no reaction is taking place, which is nothing further from the truth. The fact that we have a CSTR, that is a reactor, so reaction must happen. The reason why this happened is because there are inflows and outflows, and that should have been considered, right. But what we should stop doing anyway is to think of dCA by dt or any kind of a differential equation as the definition of rate law. This particular definition, dCA by dt, is only valid if you consider a batch reactor, that too having a constant volume, right, and therefore it is not a good idea to use this in every case. In fact, it will not work for the continuous reactor. The actual definition of rate law is right this. Even for the batch reactor, we are still going to use this rate law. What you may have, for example, if you have the first one, is you will have dCA by dt is equal to minus kCA. So, this expression comes from the mole balance of batch reactor, and we will take examples of reactors when we get to that. So, this is a mole balance. The rate law is something like this. The rate law is an algebraic equation. Rate law is not the differential equation. And what is also very, very important is rate law is independent of the reactor type. Whether the reaction is happening in a CSTR, a PFR, or a batch reactor, the rate law that defines how the chemical reaction rate depends on the concentration, that expression of rate law will not change with the reactor. Of course, depending on the concentration present in the reactors, the rates can be different, but the expression of the rate law will not be different for a CSTR or a PFR. What is not possible, that some reaction happens to be first order in the case of a CSTR and second order in the case of a PFR, that is not possible because the rate law is independent of the reactor type. So, there is one other thing that is also commonly used, that is the Arrhenius equation, and this defines the dependence of the rate constant on the temperature. So, here the rate constant is defined as some pre-exponential factor. It is also sometimes called exponential factor, pre-exponential frequency. It is also sometimes called frequency factor, exponential of minus EA by RT, where EA is the activation energy, typically defined in joules per unit mole, and temperature is in Kelvin, that is very important, and is as usual the gas constant. So, this rate constant clearly is going to increase with temperature, and in fact, if I want to expedite the reaction, this is one of the common ways. And we have discussed earlier that the activation energy can be lowered by the use of a catalyst. That is another control we may have, using catalyst to lower activation energy to increase rate constant, or by simply increasing temperature we can get the rate constants to a higher value. Now, we come to the notion of chemical equilibrium that is defined for reversible reactions. As we already have defined earlier, a chemical equilibrium is defined when the forward rate, the rate of forward reaction, is equal to the rate of the backward reaction. And once chemical equilibrium is achieved at that point, and after that the concentration of reactants and products remain constant. What I have said already earlier is, in the kind of energy diagram which I have drawn, I can in fact define the activation energy of the forward reaction as something like this, which is my EA, but I can also go back following this path, and there we have a larger barrier, but still we can define the activation energy as something like EA plus delta G, where delta G is the energy difference, the Gibbs energy difference in this case, between the reactants and the products. So, with that I can in fact define something known as an equilibrium constant. How we get it? Basically, we set the forward rate is equal to the backward rate, right. So, let us say, for example, just for sake of argument, if the reactions are first order and it is something like A going to B, then the forward rate is going to be something like KFCA, and this will be set equal to KRCB, and then K is equal to my KF by KR, and that is equal to CB by CA, right? If it was a second order reaction, then also the similar thing holds true. There we will have KFCA square is equal to KRCB square. K, equilibrium constant, is still given as KF by KR, but now we have something like CB square by CA square, right? And for KF and KR, I just put it in superscripts now. We still use that Arrhenius equation, and if we do that, we can get a relation like this. And provided that I take this pre-exponential factor to be the same, I can recover the relation that you may have seen, delta G is equal to minus RT ln of K, right? You may find this thing a bit arbitrary, because A going to B and B going to A are two different reactions. There is no particular reason why the pre-exponential factor has to be the same in both these cases. In fact, it is not same, but the problem is that we are using a wrong theory in the first place. Arrhenius equation is not the most correct theory. The most correct theory, the better theory I would say, is the transition state theory, and if you use that, in fact, you will not have to make an assumption something similar to this, right? But this equation is something that is more standard. It's used a lot. Delta G is equal to minus RT ln K. That is fine, but the derivation that we did based on the Arrhenius equation is not completely correct. It required this particular assumption AF equal to AR. So there is an alternate interpretation of chemical equilibrium in terms of chemical potential. That is, this idea of chemical potential should be fresh in your mind, because we discussed thermodynamics in the last class. So let us consider this simple reaction with stoichiometric coefficients nu A and nu P, and species A going to a product P. From stoichiometry, we can define something like this: the change in the number of moles of A by the stoichiometric coefficient of A with a minus sign is equal to the change in the number of moles of P by the stoichiometric coefficient P, and this I can define as the extent of the reaction. If this delta zeta is higher than 0, that means my delta Na is less than 0 and delta Np is higher than 0. This means we have a forward reaction. On the other hand, if delta zeta is less than 0, then the opposite happens: delta Na higher than 0, delta Np less than 0, and what we have is a backward reaction. Now recall from the earlier discussion we had in the last class that the dz is equal to this quantity. If I keep the temperature and pressure fixed, then I can drop the first term and the second term, and I am left with this. And now I have essentially two species present in the system: A, the reactant, and P, the product. So the delta G for a certain duration of reaction is given as something like mu I delta Ni summation, and that is equal to mu A delta Na plus mu B delta Nb. And since delta Na is coming like nu A into delta epsilon, and delta Np is coming as nu P into delta epsilon, we can in fact write delta G by small arithmetic manipulation as delta mu into delta epsilon, where delta mu is defined as something like this: mu P, chemical potential of P, multiplied by the stoichiometric coefficient of P, minus mu A, chemical potential of A, multiplied by the stoichiometric coefficient of A. In this particular case, I have only one reactant, only one product, but I can extend this idea, and in general, I still can write delta G as delta mu delta zeta, but then I need to sum over all the products in the first term and all the reactants in the second term, right? So now I can think of my Gibbs energy change in the following way, right. So, let us say I look at the absolute Gibbs free energy and I plot it against this extent of reaction epsilon, right. So, now if I am going in the backward direction for a reverse reaction, my delta epsilon is less than 0, right. So, in that case, the reaction is going to happen if delta mu is higher than 0. Why is that? Because delta G is defined as delta mu delta zeta, right. So, if for example, we are having a reverse reaction, then my delta zeta is less than 0. So, my delta mu must be greater than 0. Why is that? Because just like I told you, for an isolated system, we must go for maximizing the entropy. For a system where we are dealing with the Gibbs free energy, the temperature, pressure being the independent variable, we should try to minimize the Gibbs free energy, which corresponds to delta G less than 0 is a favored process. You must have heard this in various contexts. So, whenever something lowers G, that will be the favored process, just like whenever something increases the entropy, that becomes the favored process. And it is not very difficult to see why one is maximized and other is minimized, because my G is defined as something like H minus Ts. So, if entropy is maximized, G actually is minimized because there is a negative sign coming in there, right. So, in order to keep delta G less than 0, delta mu has to be higher than 0. On the other hand, for the forward reaction, my delta zeta is greater than 0. So, delta mu must be less than 0, which will make delta G less than 0, right. So, basically in both these cases, you see that delta mu is referring to the slope of this curve, because delta G is defined as delta mu delta zeta, and the slope of the curve is positive when I am on this side, and the slope of the curve is negative when I am on this side. So, if I am somewhere here, then going down is favored, because going down will lead to increase in delta zeta. The delta zeta is positive and delta mu is anyway negative, the slope is negative. So, we will go in this direction. On the other hand, if I am somewhere here, then I will again have a tendency of going down, because delta mu is now positive. So, delta zeta has to be negative. So, in both these cases, I will have a tendency to ultimately fall down to this particular point, which is going to be where the Gibbs free energy is minimized. Just like in the isolated system, we want to maximize the entropy. In this system, we want to minimize the Gibbs free energy. And in that very point, the slope delta mu will go to 0 and this delta zeta will be equal to 0. And that particular state is the state of chemical equilibrium, right. So, chemical equilibrium is defined as a point where this chemical potential change, that is defined in this particular way, the chemical potential change, that actually goes to 0. So, the condition of chemical equilibrium is basically the condition of balance of the chemical potentials of the reactant and the product. And in the condition of chemical equilibrium, there is no net change in the reaction, either in the forward direction or in the backward direction. That is why delta zeta is equal to 0, and therefore, we can see there is a clear relation between thermodynamics and the idea of chemical equilibrium. In the following class, we will extend this argument to take it to phase equilibrium, where there is no chemical equilibrium as such, but there is equilibrium between two different phases, let us say a vapor phase and a liquid phase. And again, I will use the same idea of Gibbs free energy and thermodynamics arguments to make that kind of a claim. So, with that, we are done with the discussion on the laws of chemical kinetics and chemical equilibrium. In the following lecture, we will start discussing about the phase equilibrium, and then we will discuss the idea of degree of freedom, and we will also discuss about representations of processes and so on. So with that, I stop here. Thank you so much.